Good afternoon. I welcome you to this very interesting and beneficial video here. Calculus proofs made easy. We will be looking at two of them. And they are mentioned right here, A and B. When I'm using the word show over here, we can also say prove. The first one, prove that the integrating by parts technique of integral calculus is directly related to the product rule of derivatives. You're going to be proving that integrating by parts technique is related to the product rule, which is a very interesting technique of differential calculus. And we're not proving that they're equal to each other, we're saying that they're related to each other. Likewise, number B, prove that the chain rule of derivatives is directly related to the polynomial substitution technique of integral calculus. We know these techniques are related to each other, we have to prove that they are. So the very first one, we have to prove in no uncertain terms that the integrating by parts technique, we know what that is. Integral of u dv is equal to uv minus integral v du is directly related to the product rule of derivatives, where if you're doing a derivative of a product of functions, you are getting something like this, and we have to prove the relationship between the two. And I want to show you that these proofs are very easily, we're going to do it in a very good, simple and fast manner. If this is what we're starting with, everything right over here, and we know u is equal to f of x, du is equal to the derivative of that f of x dx, v is equal to g of x, and derivative with respect to v is equal to the derivative of g of x, of course. And this is us proving this relationship over here. We look right over here, we substitute these letters into place. We have over here f of x, we have f of x integral g of x dx is equal to uv, which is just f of x g of x, and minus integral of v du. V over here is g of x, and du of course is derivative of f of x dx. We have established this. We rewrite this expression such that we're equaling it to f of x gx. This thing gets pushed on the other side, and let's show you that. F of x derivative of g of x d of x plus the integral of g of x derivative of f of x dx is equal to f of x gx. Now we have established this into a good form. And what happens next? We use a property of the fundamental theorem of calculus, which states that the derivatives and the integrals are inverses of one another. Each undoes the effect of the other. You do a derivative of this entire expression, you're basically doing a derivative of an integral. But we can rewrite this such that we can isolate the derivative procedure to portions of this. You see, I'm going to parenthesize this part. We're doing the derivative of this, and likewise we're doing the derivative of this expression, but I'm just putting it right over here because I don't have space after the equal sign. If you were to take the derivative of this entire integral expression, it would be no different than you doing the derivative of this product of two functions. Why? Because the product of these two functions is equal to all of this. So essentially all of this boils down to you doing the derivative of a product of functions, which if you were to utilize the product rule, you end up getting g of x times the derivative of f of x plus f of x times the derivative of g of x, and the proof has been completed. We have shown and clearly related that this right here is equal to this. The integrating by parts technique is directly related to the product rule of derivatives, and it wasn't too hard, and you can see that it has been done right before you. Now for the second one, we have to prove in no uncertain terms that the chain rule of derivatives or differential calculus is directly related to the polynomial substitution technique of integral calculus. How can we do that? Start with the composite function. You know f of g is same thing as f of g of x. This right here is nothing more than a composite function. If you do the derivative of a composite function, you are looking at something like this. You're doing a derivative of this. Make a substitution. U is equal to g of x. Suddenly we're doing the derivative of this f of u, right? But we have to do this in terms of the chain rule, because if u is equal to g of x, then function in regards to u takes you down the chain rule procedure. So let's do that. D over du f of u, and then du over dx, because that g of x was plucked out by means of the chain rule, but you have to readdress it in terms of its derivative, and you're doing the derivative of that. It's right here as a chain rule, nothing more than the chain rule. The derivative of f of u would be that function with regards to u but with the derivative sign on it. Derivative of g of x is this, g prime x. bring these together in terms of the substitution back over here, you're ending up with a substitution for u, which is g of x, coming back in here, you get f prime g of x times derivative of g of x. That exactly is the derivative of a composite function. Now we do a very interesting procedure over here, which is derived directly from the fundamental theorem of calculus, integrals and derivatives being opposite sides of the same coin, each being the inverse of the other. What you do here is now the integral of this derivative, and let's write it out. We're looking at the integral of all of this. Everything you see over here has been derived from here to the chain rule procedure. Now we're doing the integral of all of this. Make a substitution. U is equal to g of x because we have a composite function here. Then du is equal to derivative of that with regards to dx, and dx is equal to, you take this on the other side, du over derivative of g of x. Bring this substitution right into here and we'll show you what happens. You have f prime u, right, because we've substituted the u, and then we have derivative of g of x, and prime means the derivative of the original function, which was g of x. You have du over prime g of x, which is the derivative. These cancel out, so essentially you're looking at now just this, the derivative of function with regards to u du. Now what have we actually done? Now we're looking at an integral of a derivative. The integral of a derivative will lead you to an antiderivative, which will be your original function. Think about it, we're doing an integral of a derivative, and that should lead you by means of the fundamental theorem of calculus to an antiderivative, because you're negating each other, you're going to an antiderivative. And when we do that, what will the antiderivative of this be right here? It will be exactly the original function with regards to u, and this right here will equal to f of u. Resubstitute f of u for what it was, coming back right over here. You're looking at f of u, which is f of g of x, and that right there is showing you exactly what you start to do over here, and that completes this proof. In words, let's verbalize this. You start with a composite function, you take its derivative, you end up with a derivative of that composite function. You take the derivative of that composite function, you apply the polynomial substitution technique only to end up back at the original composite function, which you can easily set up as that, which is what you see right here. So why does this proof work? Because it shows you the direct relationship between the chain rule of derivatives and the polynomial substitution technique of integral calculus. If you didn't have this direct relationship, you could never have taken this loop where you started with one thing and you ended up with exactly the same thing utilizing both procedures. The fact that you end up with your beginning item and the product being the same, it means that there is a direct relationship between the two procedures, and that completes this proof over here for us. And with that, we end this video. Hopefully you enjoyed this one. Thank you for watching. Have a nice day.